3.4 and 3.5, and I'm going to show you a trick with using Laplace transforms to solve things that is really cool. The book talks about characteristic functions, but it's not very useful.
Say concept-wise, we most important to study for this.
There is no one to solve. It's everything. It's comprehensive. I mean, you've got to understand Venn diagrams, conditional probability in the general sense. You have to understand all of it, and you'll notice it's starting to all come together.
Yeah.
So it's everything, in my opinion. So this is section 3.4. And in 3.4, I don't know if you look carefully at this, but this is interesting because now what we're talking about is relating something about, we're actually talking about the relationship between two functions if they're not statistically independent. So I'm going to put this down here. And what actually happens is if you take the expected value of x and y, you know, what you're really doing is technically it's a double integral of x times y right here. That's f of xy dx dy over the actual entire region. I'll just put this. That indicates over everywhere it could be to get the average value, or to get the expected value of the product. Now, if you go through this and break this up, you can write this in terms of a conditional probability. And at the end of the day, here's what happens. Now, the proof is in the book. We could go through the whole thing. But what you end up getting is this, and I'm not going to do it with the variables he uses, but he said what actually happens is you get something called rho here, and this is the actual, I think he calls it the correlation coefficient. And what this is it's something that weighs, yeah, I remember doing this, right? Y'all remember this? I put it up there. And what this is, and this is real important, so this is the expected value of the product, xy. Now, if x and y are not statistically independent, this will have a value that will be non-zero. And then it's going to be minus x bar, y bar, we can prove how to get this, over the actual sigma x, sigma y. Didn't I put that down last time? Now this is real important here. So here, if we have variables x and y and they are dependent on one another, in other words, x depends on y depends on x, then you get this. Now, by the same token, listen to me. Let's assume this is general. If they are statistically independent, then if you look at this, rho equals 0 is equal to the expected value of the product of xy minus x bar minus y bar over sigma x, sigma y. If you just follow me on this, you're going to see something that you already know. You with me, class? That's 0 now because they're statistically independent. Well, I can get rid of sigma x and this should be sigma y. Right? I can just multiply that times 0, get rid of it, right? So let's get rid of that. And then you can see the expected value of x, y here is just equal to x bar, y bar. That's something you already knew. If they're statistically independent, the mean of one times the mean of the other function can be multiplied together to get the mean of the product. That's important. And usually in the book, or in some other books, I don't know about Bonslet, but what you'll see is x, y, and you'll see a bar over both of them to show this value, expected value of x, y. With me? Now the best way I can think of to actually see this in action, we're going to do a problem 3-4.1. So can you read that?
Two random variables have mean of 1 and variance of 1 and 4, respectively.
So these are the conditions, right? Now keep going.
Their correlation coefficient is 0.5.
All right, so we have 1/2 as the correlation coefficient.
And then find,
Hold up before you begin. I'm just putting this down. Rho is equal to the expected value of xy minus x bar times y bar over sigma x sigma y. I want to leave that as the formula I can reference. Matter of fact, I'll even label it. I'll call this 1. All right, go ahead.
Find the variance of their sum.
Y'all hear them? So they want the variance of their sum. So they want the expected value of quantity x squared plus y squared. You can call that z if you want. It doesn't matter at this point. I'll just say z is equal to x plus y. Create a new variable because it's a sum. So if we do this, we want the expected value of that. If you square that out, it's the expected value of x squared plus y squared plus, and then it's going to be 2 times yx, right? And I'm just multiplying that out, and I hope everybody can see this. All right, now I can say this is the expected value of just x squared bar. I'm just rewriting it in terms of shorthand. Plus expected value of y squared bar plus 2 times the expected value of yx bar. That's right. Remember this. If you have a mean squared value, that's equal to sigma x squared plus the mean value squared. Sometimes they just put sigma x squared is equal to x squared bar minus x bar squared. It really doesn't matter the form it takes. So now I come down here and I can say that this right here, remember this is effectively, I created this variable z, it's the expected value of z squared equals, all right, what is this? Well, this is sigma x squared, right, plus x bar squared. Y'all follow the thought on this one, right? I'm just replacing this with this, because that's from over there, right? Then, what about this? Well, then it's equal to plus y, or I should say, sigma y squared plus y bar squared. That's the average value squared. Then it's plus 2 times the expected value, and I'll even put expected value down here so you can't mistake it, of the product of yx. So coming over here, I have a correlation coefficient of 1/2, and I know that's equal to the expected value of x times y. In the book by Cooper and McKillum, they use E of xy typically, minus x bar, y bar, over sigma x, sigma y. Now what I'm after is, I want to get this, and I want to replace it. That's all I want to do. With me, you're going to see something here that's nice. Put the values in over here. So I have sigma x times sigma y, and I'm going to multiply over here. Sigma x, sigma y. Right? And then I'm going to take sigma x, sigma y here, divide by 2, and it's going to be plus x bar, y bar equals the expected value of xy. I'm just putting it in there. I'm going to take this and put it in this equation. They want the expected value of this, of the product of y plus x squared. So that's equal to sigma x squared plus x bar squared plus sigma y squared plus y bar squared. That's the first terms here. And then plus 2 times that, right here. So it's 2 times the quantity, and it's going to be sigma x, sigma y over 2. And then it's going to be plus x bar, y bar. I just wrote the whole thing out so there's no mistake about what I'm doing. Okay. Now, we can put the values in if we want, but let's see what we can do with it. Yeah, why don't we put the values in? So what is sigma x squared? What was the variance of sigma x? 1? From over there, guys? Is that right?
Yes.
All right, what's the mean Mean value of x?
1,
What's the, sigma squared is 1?
4.
Of what?
Variance of y is 4.
All right, what, and the mean value?
The variance of y is 4.
I heard variance of y is 1, and variance of y is 4. What is it?
4.
4. So the variance over here is 4 plus mean value 1?
1.
All right, 1 squared is still 1, plus 1. Then it's plus 2, right? Let me go ahead and do this. So this is going to be sigma x, sigma y. Well, actually, why don't I just do this? So if I go ahead, I have 2, and I'm going to put it in. Sigma x is equal to, now that's the square root of that. Sigma x is 1, sigma y is 2, right? So it's 2 over 2, which is 1, plus x bar, y bar 1, so it's plus 1. And you can see the only thing I've done is substitute the values. Isn't it, class? Isn't that 11? You tell me if I did something wrong. That should be the mean value of x plus y squared, correct? Is that what they're asking for, by the way?
Find the variance of their sum.
All right, now that's not the variance, is it? That's not the variance. That is the mean squared value of their sum, isn't it, class? So this is actually this value. Now, if I want the variance of z, it's just z bar squared value, the average value, that's what we got. What? Minus what? Z bar squared, the average value squared. Now, I don't want to go too fast. Everybody see what I'm doing. I'm just using z to represent x plus y. And you could write this, and he does in the book, as sigma of x plus y instead of squared, instead of putting z, but z is easier. It makes more sense to me. And you could say, well, we could do it this way. They'll be the same. So we got the mean squared value here of 11, right? Minus then the average value squared. So z is equal to x plus y right here. I want to take a moment and make sure I make this point clear. What is the average value of z? Or the expected value of z? Well, this is additive, right? It's not a product. Do you agree with that? If it's additive, this is just x bar plus y bar. That's all it is. Now, if there was a coefficient a there and a coefficient b there, then it would be just a times x bar plus b times y bar for the expected value of z. With me, or the average value of z? Now, and what is that? Well, x and y both have expected values of 1, so this is 2, isn't it? So then if we take, and we want this is going to be, that's it. I mean, that is the right answer, though. Now, what else are they asking there?
Find the mean square value of their sum.
We got it right there, 11. They have 10, right?
Yeah, find the mean square value of their difference.
Okay. If you want the mean squared value of their difference, that's the sum, right? The difference would be what?
The mean square value of their difference.
Okay, so then when I do that, this is going to be this value, right? And that would be x squared plus y, x squared bar plus y squared bar plus, minus 2 times x, y bar, or the expected value of x, y. Same as before, to get this, x squared, the value of that is just sigma x squared plus x bar squared, plus y squared is just sigma y squared plus y bar squared, minus 2, and then over here, I have the expected value of that. I'm going to put a number in for this. So the expected value of x, y. I hope we didn't make a silly math error. So this is sigma x, sigma y. Sigma x is 1, sigma y is 2, so it's 2 over 2. I'm just doing the reverse order. So taking this, plus x bar, y bar is 1. So that's 3. Wait a second. That's 1 plus 1 is 2, correct?
Yeah, that's what I was asking.
My bad. Over here for this one, this is 2, so instead of plus 4, How did I get minus 4? Oh, sigma z, never mind. That's 11. All right, let's see what it is. So for z squared bar, sigma x squared is 1, x bar is 1, sigma y squared is 4, plus y bar squared is 1, minus 4. And if I look at this correctly, unless there's something wrong, the 4's cancel, right? And I get 3 for the mean squared value of their difference. Is that an answer? Then I have a feeling that thing's wrong. This is straightforward, and we've had a few exercises that had wrong answers. I believe that's wrong. So this is problem in the back, 3-4.1. This is the one in the notes, Tom Denny's notes.
Two random variables have 0 mean.
All right, x bar equals y bar equals 0.
One has a variance of 16,
All right, sigma x squared is 16, and sigma y squared.
36.
All right, before I do anything more, that means sigma x is equal to 4 and sigma y is 6. I don't want to mess that up.
Their relationship, their correlation coefficient is 0.5.
All right, so they say rho equals 1/2. Go ahead.
Find the variance of their sum.
Okay, so what he wants is a variance. So he wants sigma squared of z. I'm using z to represent x plus y because it's the shorthand form, and you're going to see he's going to use it more and more in the next section. So now I'm going to start with that correlation coefficient, and I know rho is equal to the expected value of x times y minus x bar y bar over sigma x sigma y. That's just by definition, correct? X bar y bar equals 0. I can get rid of this, can't I? Now, if that's 0, I can say the expected value of xy is just sigma x sigma y times rho. And what that means is the expected value of x times y is equal to x y bar. I'm writing it both ways just to make sure I'm complete here, and so if you're looking through your notes at some point, but you're distracted in class, hopefully it's the ring bells. So that equals sigma x times sigma y times rho. Rho is 1/2. Sigma x is 4, right? And sigma y is 6. So what is that? That's 24 over 2 is 12. You agree, class? Okay, now for sigma z squared. First, I better do this. Z squared, just z squared itself, is equal to x squared plus y squared plus 2yz. And I hope everybody sees that without any problem. 2yx. I did have coffee. Now I'm going to go ahead and just do this. And then over this. Okay. All right, next I'm going to replace x squared bar, y squared bar with their standard deviation and mean values, right? So for this, z squared bar is equal to, and here it's sigma x squared plus x bar squared plus sigma y squared plus y bar squared plus 2 times the expected value of yx. Now, do you mind if I just put in the 12 because we found it? So this is 2 times 12, and I want to put it there so if you're writing notes, you'll see what in fact I did. I just substituted that value. Now we're going to do them all. We're going to substitute everything. Sigma x is equal to 4, and squaring is 16, plus x bar is 0, which is nice, so we'll get rid of the x bar and y bar. And it's plus 36, right? And then it's plus 24. That's z squared, but did they want the mean squared value of the product?
The variance.
The variance. So how do you get the variance? Perry, be attentive here. Variance, again, of sigma z is the same thing as sigma quantity x plus y squared, right? Or x plus y, pardon me, squared. The variance of the product. And what that is going to be is z squared bar minus z bar squared. So look over here. What is z bar down here? Or What is the average value of x plus y? It's 0, because the average value of x is 0, the average value of y is 0, correct? So, back to this. We get this, and what is that going to be? I think it's 76, yeah. And is that right?
Yeah, 76.
76, we got one. All right, so check that box. What else is this for? The next part is the variance of the difference, right? What's the only thing we change here? When it's a difference, this happens, right? If it's a difference, what happens here? You don't even need to write this down. What happens down here? That and that stay the same, but this becomes minus, right? Minus, now what's the answer? That's 28. You agree with that? 28. So that means now I have, and I'm calling this z, maybe I should call it z2 or something like that. So you can differentiate. So what is this going to be? Now sigma of z2 squared is going to be still z squared bar, but it's minus z bar squared, right? What is z bar squared? Doesn't matter. Plus anyone.
0.
0. That means, so this is just going to be, unless we did something wrong, 28. Is that right? Is that the answer in the book?
Sure is.
Okay, good. Thank God. What's the next part?
Repeat A and B if the correlation coefficient is negative 25.
Now, I don't have to go through every permutation, but you see the only big difference over here is now there's going to be a negative here, right? You with me? If the correlation coefficient rho is not 1/2 but minus 1/2, this becomes negative, right? All right, if that is negative, what happens? That is negative, right? It's minus 12. Y'all follow me? The negative sign just carries through. Can you do that one on your own? Everybody? Please do these things, because there's little subtleties you're going to see. This is straightforward, it's easy. I want to do the next one too before I move into section 5. 3-4.2. Go ahead and give me the value.
2 statistically independent random variables.
All right, that means the coefficient rho of xy equals 0. All right, so these are statistically independent random variables. Go ahead.
X and Y. And
Sigma x is equal to what?
9, and sigma Y is equal to 25.
Okay, hold on for 1 second. I'll put down sigma x is 3 and sigma y equals 5, just so I don't mess up.
U equals 3x plus 4y.
All right, please be attentive here. Now we're creating these new random variables based on the first two. 3 what?
U is equal to 3x plus 4y.
And v, that's u.
5x minus 2y.
With me? These are new, you're going to see something here. Now remember, those are uncorrelated, but these don't have to be uncorrelated. Maybe they are correlated. With me? So what's the first thing? So they want the variance of u and the variance of v. The expected value of u squared, that's the expected value of 3x plus 4y quantity squared. That's the expected value of 9x squared plus 16y squared plus, and it's going to be 12 times 2, 24xy. I'll stop for a second. I just squared that out, right? So that would be the expected value of 3x plus 4y squared. Do you agree with this, everyone? And this is the expected value of u squared. You can put it down as just u squared bar. All right, now what is that? So I'll put it up here. So u squared bar is equal to what? Well, it's 9 times x squared. I'll write it down, then I'll put it on here. So 9 times x squared, the expected value of that, plus 16 times y squared, expected value, plus 24 times the expected value of xy. You understand? I'm just rewriting it there. Now, what do I do next?
Then
Remember, they gave us all the information we need. The mean, did they give us the mean values here or no? No, that's good. This is perfect. So you don't need the mean values, you're gonna see this. So, but I'm gonna put them down, but you'll see how they cancel. So this is u squared. So now I have this equals 9 times, and this would be sigma x squared. I'm gonna leave it as sigma x squared. You're gonna see why I'm doing this in a second. This is sigma x squared plus x bar squared, right? Plus 16 times sigma y squared plus y bar squared. And it's plus 24 times the expected value of xy. Well, what is the expected value of xy if this is true? Rho xy is equal to the expected value of x times y, right? Minus x bar y bar over sigma x sigma y, right? Isn't that right? All right, this is 0. So if I multiply 0 by this, I get this, right? That means the expected value of xy is not 0, but x bar, y bar. They're uncorrelated, so it's the expected value of the first times the expected value of the second. What is the expected? So now I'm just going to put that expected value of the first, which is just x bar, times the expected value of the second, y bar, right? And remember, that's u squared. And I'm going to tell you what, let me leave that alone. That's u squared, right? This is all right here, u squared, you're going to see this. So this is u squared bar, that's what we have there. But they asked for variance. So what would the variance of u be? Well, it would be u squared bar minus u bar squared, correct, class? We've got u bar squared here, right? Now we're going to subtract from this so I can get the variance. I want sigma u here. I need what u bar squared is. That's u, right? What is u bar? 3x bar plus 4y bar. Take that, you got to square it, right? So now, u bar squared is equal to what? 9x bar squared plus 16y bar squared plus, what would it be? 24x bar y bar. Agreed? You're going to have to help me here. So now I need to subtract that u squared right here that I gave you. So what am I going to subtract? Can you read that to me?
9x bar squared
Go ahead, plus.
16y bar squared plus 24x bar y bar.
Can everybody follow me? And that right here, this part is just u bar squared. You're going to see the cancellation is perfect. I got 9x bar squared minus 9x bar squared. Gone. I have 16y bar squared. I have 16 minus 16y bar squared. Gone. Agreed? I have 24x bar y bar minus 24x bar y bar, right? Gone. What am I left with? Let's get rid of this. What you're noticing is what? It's in this is really the crux of the issue. Write this down. I can say that sigma mu squared is really equal to 9 sigma x squared plus 16 sigma y squared. And that's it, right? Now here's the moral of the story on this one. We'll get to the V part, but you're going to see it's the same deal that I just did here. But I'm going to write this down, and it's in the book. It won't matter if they're correlated or uncorrelated. 3-28. And here, what do they have? if you have variables, I'm going to add something to this, so be really attentive and write it down. They have sigma right here, squared of x plus y. You tell me if I'm wrong. Do they have that?
They have a sigma x plus or minus y.
All right, well,
It's
it's
all squared, yeah.
yeah, but it's a variance. That's equal to sigma x. We're going to change this in a second to take it to account for everything. Plus sigma y squared. And then it's going to be plus or minus 2 times the correlation coefficient, right? And then it's going to be what?
It's gonna be, so you got that, plus or minus 2 rho,
Sigma x, sigma y times y.
that's it.
Can you all see this? Now, this row here should have a sub xy, so it's the correlation coefficient of x and y. But this assumes they're linear. X as the coefficient is 1 and y's coefficient is basically going to be 1. If you change this, it's not in the book, so write this down. If you want the standard deviation of ax plus by, then you have to go over here and you have to say it's going to be a squared sigma x squared plus b squared sigma y squared. Then it's plus or minus, and it's going to be 2 times rho x, rho y, sigma x, sigma y, but then it'll be times a times b. Now, and here, see how it got a coefficient and b coefficient. He doesn't add that in there, but it's so important because now if you have that, remember the way I did it, I worked out the mean squared value of, it would be in this case, it would be ax plus by squared. Then after that, I went through the rigor of going ahead and saying, if I have that, then if I want to find the standard deviation of ax plus by like this is, I have to find the mean squared value minus the mean value squared, right? When you do all that crap, this is what you get. So write this equation in your book and put it down because you're going to use it. We're going to do the next part based on that. For the answer we should get for the first part, and you got the solutions down here, it's going to be 9 times sigma x squared, which is 9. That's going to be plus 16 times sigma y squared, which is 25. That's a big number. What is this? 481? Is that right?
That's right.
Now for part V, to get the V, remember that was for u. So what is V in this one again?
5x minus 2y.
We're not even going to bother doing it the long way that I did it before. What I'm going to do is simply go ahead and note that this works. Okay. So my A is 5, and my B is going to be minus 2. You agree with me, class? Now we go down here, and so if I want sigma squared of 5x minus 2y, which is the same thing as sigma squared of v. All right, so what is it? Well, according to that, it's a squared. A is 5, so it would be 25 times sigma x squared. I'll write it down. We'll put in the values in a second for that. And then it's going to be plus, it's always plus there, b squared, which is 4 times sigma y squared. Then it's going to be, now that's a minus sign, so it's going to be minus 2 times the correlation coefficient, that we'll talk about in a second. Correlation coefficient of x, y. And then it's times sigma x, which is 9, times sigma y, which is 5. And are x and y independent?
Or wait, wouldn't that be 3 spot? It's just sigma x and not sigma x squared.
Yeah. You're right. 3. That's why. I can be more attentive to whatever. You all with me? But my point is, what did they say? X and y are uncorrelated?
Yeah.
All right, what happens to this?
Disappear.
That's right, it goes away. So what is this going to be? 25, right? And sigma x squared is 9. plus 4 times y squared is 25, right? And what is that gonna be? Let's see, it's 100, and that's, is that 325, class?
225. Oh, the total is 325, yes.
325, is that right?
Yeah. That's right.
But you'll note one thing, it's a lot quicker doing this. Now, if that correlation coefficient wasn't 0, which happens all the time, then you're gonna have to put the correlation coefficient, wait a second, that's just rho xy, I gotta do it twice, rho xy. That correlation coefficient has to go in there. And remember, if it's plus, if the correlation is plus, you keep the plus sign. If it's minus, you keep the minus sign. 3-4.3.
Yeah. Random variable x is a variance of 9,
Oh, keep going.
and a statistically independent random variable of y. Or y has a variance of 25.
Stop. If the statistically independent rho xy is 0, period, right? Keep going.
Their sum is another random variable z equals x plus y,
Uh-huh.
without assuming that either random variable has 0 mean.
Still, sigma x squared plus, I mean, if you want, they want the variance, right?
They want correlation coefficient of x and y.
It's statistically independent, it's 0
Yeah,
for x and y.
and then
Is
the
that the right answer?
Yeah.
Okay, go ahead.
correlation coefficient between y and z.
Now that's different because z is equal to x plus y. They will be correlated. Can you guys handle that one? The looks I get, it's like, handle what, man? I don't blame you. Would you do me a favor? I'm going to give you some of these problems. If they follow the same trend, write that down.
Okay.
That's your go-to right there. That says it all. You don't have to go through the long, arduous thing I did in the beginning. So now we're going to the next section, which is 3-5 point. It's going to be section 3-5. Here it's 2 variables, but they're going to say, if you look in there, it's z is a function of z is equal to y plus x or y minus x, and they want to find f of z. So this is important. It's a little hairy too. If you read this, it's going to be something called convolution. If I have time, I'm going to show you some really cool tricks. And you'll thank me because the book does not do it this way. They use a characteristic function. It's a Fourier transform in reverse. But you can use Laplace transforms to beat these problems faster. So we're going to have z is equal to x plus y. These are 2 variables, correlated or uncorrelated, right? But now, or statistically independent, I should say. We're going to say something about this. The only thing I care about, we just did the ones where we had a correlation coefficient, right? But this is important. So if they aren't, say, if and only if x, y are statistically independent, then we can do this. We can say we want an f of z. That's what our goal is. So we can say, and the way he does it, I'm going to try to replicate what he has in this book. We can say, well, let's talk about, the way we always go through is the general formula for the probability. So the probability of z, and it's usually a random variable z being less than some z, is the same thing as f of x plus y being less, these would be random variables, x plus y being less than small z. They're the same thing, right? This is the same thing as the probability of z, random variable z, less than small z. It's the same exact thing. So now, we can say that this right here, if they are statistically independent, I can say that that is equal to a double integral of f of x, right? F of, let me do it this way, xy, just watch and don't do anything yet. I can say it's dx dy And because we have x plus y equals z, and z will be known, we can say that x itself is going to be y minus z. This is the key. You agree with that? If you say z is 3, it's known. If I want the probability of z less than 3, it's x and y less than 3. But that is a contour. It is not, doesn't have straight edges, you might say, on that, if we drew this thing. So from here, for x, it's going to go from minus infinity to, and this is going to be z minus y. And for dy, it can go over the entire range from minus infinity to infinity.
Where did that 3 come from? Where did the 3 come from?
Z.
So,
So I'm trying to show you a script z.
okay.
I'm sorry. I'm trying to see there's the random variable is capital Z.
Yeah.
Small variable z is a known value, a specified value. That's all I'm trying to say there. So if you take this, and this is my capital F z of z now, and that would be, then to get f, small f of z, the probability density function, f z of z, this is the probability density function now. What I need to do is take a derivative of f with respect to z of z, right? I want you to just follow me on this one. So I come over here and I look at this thing. The y integration doesn't seem to have isn't a factor, but when I take a derivative of this, the only thing that depends on z is the upper bound. Do you all see this, class? And if you take a derivative of the upper bound, you get 1 with respect to z, right? And if you remember that Leibowitz's rule, you take the derivative of this boundary, if we're doing f of z, derivative, and then you evaluate this by replacing x with z minus y. Do you remember this? As a matter of fact, let me do it this way. I'm going to expand it a little more. So this is the integral from minus infinity to infinity. Here it would be f y of y. They are statistically independent times the integral from minus infinity to z minus y of f of x dx. And do you agree with this? If they're statistically independent, f of xy is equal to f of x times f of y. Agreed, class? Now, when you take a derivative of that, this is left alone. This is a derivative, the upper bound with respect to z is 1, and then you have to evaluate this, replacing x with the upper bound. So you end up getting this. I'm going to ask something. So I get minus infinity to infinity. Now it's fy of y times fx of z minus y dy, right? Does anybody recognize what that is the form of? It's convolution.
Yeah.
That is literally something that should jump off the page for you. So you can say f of z, if they are statistically independent, is simply going to be the convolution of f of x, right, times f of y. This is the convolution symbol. It's an asterisk. Do you agree with this, class? That's all it is. If you catch that, and then I'm going to do a problem. How do you always solve convolution problems if you're allowed to?
Loss.
Amen. Is at the end of this chapter that he talks about the characteristic and function. Forget the characteristic function. Remember, it's convolution of the two. Say g of x is the convolution of y of x convolved with L of x. Convolution is something you guys have probably done a fair amount of. At least you've been introduced to it. And my way of always doing it is, and I like to do it with showing the plots where you find the variable that has the most going on, you don't flip the axis, and take the other one, you flip it, and then move the window through. Now that's, I'm not saying this precisely, but I think you get this. So in the exercise, give me the exercise.
Random variable x has a probability density function of f of x equals 2x between 0 and 1.
2x between, I didn't do this one, 0, x, and 1. Is that right, class?
Yeah.
All right, keep going.
And it's 0 elsewhere.
Yeah, I got
And then
0 else.
independent random variable y is uniformly distributed between -1 and 0.1.
All right, so it's gonna have, 1/2 is the value, and it's between -1 greater than y, less than 1?
Yeah.
With me? Now, these variables, and I assume they have z is equal to y plus x.
They have z equals x plus 2y.
Let me, before I do that one, because it's gonna get, there's too many complicating, I'm just gonna say z is equal to x plus y. We'll do 2y in a second, all right?
Sure.
If it's equal to x plus y, and I tell you now, I know if it's x plus 2y, that my f of z is just equal to fy of y, right? Or fy. I'll just leave it as fy. I don't want to get into the z. This convolve with f of x, right? Now, you can get tripped up because there's an x and a y here. Those domains go away. You integrate that out. You with me? You're going to integrate that out with the convolution integral, right? So when I take a look at this, what I'm going to get, I'll do this part first. F of x has the most going on. This is a constant value. So now, let me actually write the value of the convolution. What I'm after for my f of z right here, technically it's the integral from minus infinity to infinity of the first variable, and it'll be f of, and I can put tau, times the second, call it f of, I can call it, let's see, f of x, and then it's going to be times fy, and this is going to be z minus tau. You're integrating out tau, d tau. Normally you're used to putting a t there, right? It's t minus tau, and then a tau in there, you integrate out tau. I put the z in there so you know the result is going to have a function of z, and this will be f of z. Okay, if you look at this one the way I do it, you got to pick one function to actually just sketch versus the argument tau, and I'm going to pick this one, f of x. With me? So that one, f of x, is 2x from 0 to 1, but I'm going to take it versus tau. So my function is fx of tau is 2 tau here, and that's just a straight line. At 1, the height is 2. Correct, class? Then, I'm going to leave that alone. Then, the way they usually do this, take the other value here, and then flip it. You'll notice when you flip this run around the axis, it's the same exact thing, isn't it, class? It's 1/2 from minus y to, from -1 to +1. When you replace y by tau, right? What I want to do is this. I want to get f of, first I want to get f of y of minus tau. When I say flip, if this had a value of 1/2 from 0 to 1, then it would start at -1. You follow me, class? It would go to 0. And it looks like this. This is -1, this is +1, right? Now, what am I going to do? To that window, it's going to start moving that way. But before I do anything, I want to show you. This lower limit is actually going to be equal to the value of z, and this is going to be the value of z. So when z is 0, that's what you get. This is actually going to be z minus tau now, and I'll explain why I'm doing it. And this is versus tau here. I know it's been a while for some of you, but you remember this general way of doing business for convolution. Remember? You start by taking your second function that you're going to use as the moving window to see where the overlap area is, and you get the product of this times that, and then you have to integrate it, right? Well, the lower limit is going to be z minus 1, the upper is z plus 1. Now you can see there's overlap right here, and there's no overlap here, but where the threshold is, where it starts overlapping, I'll put it down here, when I have z is equal to -1, then this looks like this. That would be the threshold, and I'm trying to graph that. So then it would look like this. This would be -2, this would be 0, And this would be the window for my second function, fy. And this would be of -1 minus tau. This is tau here. And it would go right to 0. I hope you can appreciate it. You agree? Okay, when you get in the car, you're going to find out just how much fun this is in trig identities. Now that's the threshold where you start getting overlap into here, right? And there will be overlap, continual increase, and basically the window will move through, and between 0 and, you might say between -2 and -1, so I'll put this down here, for z greater than -2, less than -1, the area really is going to be, the upper limit would be, well, it's z plus 1 minus 1 is just z, right? I know I'm talking kind of quickly, but you follow me on this? This has a value. Think about it. When z is -1, right? -1 plus 1 is 1. It's this threshold, right? Then when z goes to what? Sorry, I had -2. It should be -1. My bad. -1, and this should be 0. That's where this is, right here. And it's moving through, and between -1 and 0, f of z will be the integral of simply the integral from 0 to whatever it is, z, of this function right here, which is 2 tau, e tau. And that's going to be equal to, as I'm showing here, you're going to get tau squared over 2, right? Times 2 is just tau squared. And that means it's simply going to be z squared from -1 greater than z less than 0. That's f of z. Agreed, class? I'm just doing convolution of the two things, right? For the other one where they have 2y, we have to adjust that because it's not just convolution, we have to adjust it. All right, now what happens when now this window moves through? Remember, we're going from up to here. This would be z equals 0, right? Now this entire triangle is in this, and then it would be from 0 to 1, it would be a constant area. Do you agree with that? Constant area is just the area under here. But it has a height of 2 and a width of 1, so the area is 1/2 2 times 1, or just 1. So then f of z equals 1 from z greater than 0, less than 1. Finally, I don't know if I'm going to have time to get through that. What happens when all of a sudden z is greater than 1? Look at the lower limit. So this is, say it's 1.5. 1.5 minus 1 is 0.5, right? Now the lower limit on the window is here. And I'm trying to show you that now, by the way, the height of this was 1/2, wasn't it? Of that. So actually this should be that over 2. Yeah, it is over 2, and this should be 1/2, my bad. So when we do that integral that I've got here, this f of y right here has a height of 1/2. I forgot to put that in there. It's a product. You're gonna see that was the right answer for the one with the 2 there, I believe. And then finally, when you get from z greater than 1 but less than 2, then you have to take the entire area right there, which is going to be 2, or sorry, is 1, and you have to subtract off the lower area, which would be the integral from 0 to z minus 1 of, and there's a 1/2 here. I put a 1/2 in front of the whole thing. What I'm doing is getting this area here. That's the overlap area, but there is a coefficient of 1/2 I have to multiply that area by. So I get this, and that's going to be what? That's 1/2 minus, and it's going to be z minus 1 squared over 2. So it's going to be z minus 1 squared here. And that would be from 1 to 2, and finally for z greater than 2, it's 0. Now, Let me make one comment. Suppose this is x plus 2y, right? When you look at this function, x plus 2y, let's see, f of x is just equal to 2x for x greater than 0, less than 1. I think that's right, 0 else, right? And fy of y here is equal to 1/2 for y greater than minus 1/2, or I'm sorry, greater than minus 1, less than 1. Isn't that right? And 0 else. I'm just restating what it is. Correct, class? All right, now what is f of z? Well, f of z is the integral from minus infinity to infinity, technically. And I'm going to put the f of x first. So I'm going to put f of x, f of y, of z minus, maybe I do it the other way. I'm running out of time on this one. Tell you what, I'll finish this up. Here's the whole thing. Remember that integration I had right here? This f of z is going to be an integral, a double integral, and it's really of f. The way I had it before was f of x. You put this f of x of z minus y times f of y dy. It doesn't matter if it's y or x here, as long as if you're going to use the f of y as the one you don't flip, you leave that alone. If you're going to use this as the one you're going to you don't flip, then you would leave the f of x in here as the integration of x. And this is from minus infinity to infinity. Here's the difference. X here is not going to be z minus y, it's going to be z minus 2y is equal to x. Can you follow me on that, class? So you have to put z minus 2y here. And then do the integration. I don't have enough time to finish that. But all these things, you can manipulate that and get it into a convolution form. Trust me on this one. You'll just redo a function, and then you can get the answer. What I'm going to show you next time on Friday online, I'm going to use Laplace transforms to solve these. I'll give you some problems. Please do the reading.